Okay. Let me see, that was on 5. Okay, so we're gonna go over the quiz number 5. Let me go share the screen. Okay. Okay, so question number 1, if the critical frequency of a low pass filter is increased, the bandwidth will, most likely it will be increasing. Okay, so if you look at the band low pass, it would be something like this here. This is represent a low pass. And so if you said you have a cutoff would be somewhere at this point right here. So if you increase the frequency, so if you increasing toward this way, so now it's going to be over here. So therefore now you'll have bigger bandwidth. Okay, so that's when you increase. So if you increase the critical frequency, you will have an increase in bandwidth. Okay, so the answer is A as an apple for number 1. Now for number 2, if the critical frequency of a high pass filter is increased, the bandwidth would most likely would be decreasing. Okay, so we're looking at the band pass, high pass filter. So this is high pass filter. So like I said, we have a critical frequency would be right here. Now, if we increase the critical frequency, now we increase would be somewhere here. So now we have less bandwidth would be less. Okay. So that's why it's causing a decrease. So the answer is B as in Bob for number 2. Number 3, if the Q of the band pass filter is increased, the bandwidth will. Okay, so the bandwidth equal the resonant frequency divided by Q, or you can say center frequency. Resonant frequency or center frequency mean the same thing. Okay, so therefore, if you increase the Q, you would decrease the bandwidth. Okay, so the answer is B as in Bob for number 3. So any question number 1, 2, or 3? Okay, look like no question. Okay, next set. Okay, the term pole in filter terminology refer to a single RC circuit. Okay, so the answer is C as in cat for number 4. Okay, for number 5, a single resistor and a single capacitor can be connected to form a filter with a roll-off rate of. Okay, so the roll-off rate now in a single, when you are single combination, either minus 20 dB per decade, or it can be minus 6 dB per octave. So the answer A and C is correct. So the one that has the most correct is D as in David for number 5. Okay, so number 6, a band pass filter, a band pass response has. Okay, so the answer is A as an apple for it has 2 critical frequency. So band pass filter is this right here. So you have 1 critical frequency would be at the lower side here, and the other one would be on the upper side would be over here. So that's why we have 2 critical frequency. Okay. So that's okay. So that's so this one here. So you got 2 critical frequency for number 6. So the answer is A as an apple for number 6. So any question number 4, 5, or 6? Okay, no question. Next set. Okay, the lowest frequency passed by a low pass filter is it's going to be B as in Bob for number 7. Because if you look at the low pass filter, would be this one right here, low pass filter. So at this point, it's at 0 hertz, would be 0 hertz right here. So it at 0 hertz, it does register a voltage, okay? So therefore, it's at 0 hertz. Okay, so number 8, and the quality factor Q of the band pass filter response on. Okay, so that's the formula is Q equals FR divided by the bandwidth, or FR is same thing as resonant frequency, or you can say it's a center frequency would be the same thing. Okay, so the answer is C as in cat for number 8. Okay, number 9, the number of poles in a filter affect the mainly it's going to affect the roll off rate. So it's going to be able to, so it's going to be something something similar to a it will be like this here. So this is say that this will be represent 1 pole. The next one will be go right here. That will be 2 pole, and the one with the 3 pole will be pretty close to almost toward the ideal. Okay. All right, so the answer is D as in David for number 9. So any question number 7, 8, or 9? Okay, no question. Next set. Okay, number 10, when filters are cascaded, the roll-off rate, it increases. Okay, so the answer is A as in apple for number 10. Number 11, when the gain of a filter is minimum at its center frequency, it is called a band stop filter or a notch filter. So what they're referring to is this one right here, and this would be at the minimum. Okay, and this is what they call a band stop filter or a notch filter. So some books call it a notch filter and some call it band stop filter. Either one is correct. Okay, so the answer is D as in David for number 11. Okay, number 12, identify each type of filter response: low pass, high pass, band pass, or band stop. Okay, so this is the schematic of the output of this schematic, and look like this would represent a band pass. Okay, so the answer is C as in cat for number 12. So any question number 10, 11, or 12? Okay, there's no question. Next set. Okay, so identify. Okay, so we just identify. So the answer is in this one is a low pass filter. So the answer is A as an apple. Okay, number 14, this look like a band stop or a notch filter. So the answer is D as in David for number 14. Okay, any question 13 or 14? Okay, no question. Next up. Okay, so identify. Okay, so this would represent a high pass filter. So the answer is B as in Bob for number 15. Okay, number 16, what determines selectivity in a band pass filter? Okay, mainly it's the Q, it's the quality of the coil and the quality of the coil. Okay, so that's what it is. Anything that has to do with the selectivity, it has to do with the Q or the quality of the coil in the band pass filter. Okay, so the answer is A as an apple for number 16. Now, number 17, one filter has a Q of 5 and another has a Q of 25, which has narrow bandwidth. Okay, so you can see bandwidth equals the resonant frequency divided by Q. So therefore, the bigger the Q, the narrower the bandwidth. Okay, so in this case, the answer would be 25. Okay, so the answer is A as an apple. Let me go copy this. Copy, paste. So this what we have, the smallest bandwidth would be this one. Okay, so that's pretty much it. Number 15, 16, and 17. So anybody have questions? 16, 15, 16, or 17? Okay, so no question. Okay, so did someone have a question?
Yeah, Sam, I got a question. On
Okay.
the bandwidth, what, like, is it how the height of it, or is it the
No, the
width?
bandwidth, the distance between where the cutoff point would be, this one would be wherever the critical frequency is at, which is at the -3 dB, would be somewhere here. So from this point onward, this way, the signal is going to be getting passed for, the signal would be able to go through. Any signal from this point, this way, it's going to be cut off. It's going to be, it gets terminated. It doesn't get through.
Okay, thank
Okay. And so that's what you determine the band pass that. So same thing with here. So if you have the critical frequency would be here and here. So therefore, and on this side, from this point to this point, it will be able to pass. From this point to this point, it's going to be cut off or terminated. It won't get through. And then from this point to this point, it will be able to go through. So that's what so this one have a split of that band pass. So from here to here, and then from 0 to this point, it would be one a band stop filter. Okay.
Got it. Thank you.
You're welcome. Okay, any other question? So, this, anything that deal with filter is really kind of critical, because if you have a remote controls for your TV, you have remote control for your garage, it operate on this kind of filter system. Okay. That's why that's why it's essential that you understand what kind of filter system they are built into that unit. Okay. Sometimes they build using a band pass, sometimes they use a low pass, and sometimes they use a band stop filter, or sometimes they use a high pass filter. Okay. Okay, so that's pretty much it. That's covered the filter system for this quiz. Okay, so anybody still have any question? Number 1 to 17. Okay, going once, going twice. Okay, look like stay in chat. I'm trying to ensure myself to ask question, but it say host is not allow anyone to unmute. Oh, let me see if I can unmute myself. Okay. Yeah, Nicholas, you can be you can unmute yourself. You can unmute. Yeah, go ahead, Alex. Alexander.
I still don't get that zero frequency.
Okay, zero frequency. Remember, just like if you look at your oscilloscope, remember oscilloscope, you got X, Y axis. So the zero would be starting at this point right here. Okay, and 0, and then it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever to whatever the infinite amount of frequency, depending how far range it set up. Okay, so it goes from this point, it goes so positive going this way and negative going this way. But as you can see, the signal only start at the 0 point, and then you got the voltage value or your maximum voltage output possible. Okay, so it starts from 0 hertz, 0 hertz all the way to whatever the maximum here is. I do not know. We just kind of give you what a general term wise. So everything remember, we don't have negative frequency. We can only have positive frequency. Okay, so like here, you just X and Y axis. So it goes from 0 point, it goes all the way to the positive side. And your voltage, we're going to look at mainly in the positive voltage. We don't look at the negative side. You follow, Alex?
Yeah, so we have voltage at zero frequency. Got it.
Yeah, we're looking always starting at 0, going toward this way. So 0 is right here, and going toward this way is positive. Going toward this way would be toward a negative. And then on the positive side, 0 from so voltage wise, 0 from 0 here, and it goes up to positive this side, and then from this side is going toward a negative toward this side. But we only, when we deal with frequency, and we always look at just at the positive frequency. We don't deal with it. There's no such thing as negative frequency. Okay.
Okay, thank you, Sam.
Okay, you're welcome. Okay, Nick, let me see. Okay, Nicholas, do you have a question? Yeah, we want to make sure it's clear. So if it's not clear, please go ahead and unmute, and or you can type in the chat.
I got a question on homework assignment 18.
Okay. What's your question on assignment 18?
So I think you might mention something before, but I don't know. I got all the answers in. I thought I'm doing this all right. It's pretty basic, but it's still not saying pass. Was there an issue with the Excel sheet or something?
Not that I'm aware of on this one. Okay, so can you show me your Excel sheet? Can you share your screen, and then maybe I can help you? And
Well, my Zoom is on my phone right now, unfortunately.
oh, okay. Oh, okay. Well,
I can give you all my answers though.
Okay.
if you want to run through
Okay, so let me go ahead and share the screen. Then it would be more ideal. And okay, so share. Okay, so this is assignment 18. Assignment 18. Let me go ahead and enlarge that just a little bit. Okay, so okay, so this one is so assignment 18. Is this the one that you're looking at, Nicholas?
Yes, it is.
Okay, so we're gonna be looking at here. Okay, so you look at to do the calculation, like we said. So it's gonna be following this rules here. Just scroll up a little bit. Okay, so you calculate V. So first thing you want to do is calculate VD, correct?
Yeah.
Okay, so VD we have, and this one is going to be VA minus VB. So, okay, so that's why we got 10 minus the 50. You got negative 40.
Yeah.
Okay.
Yeah. So I see where the two differences are from my results to yours.
Okay.
The first one is on number 2. I have I have 90 for the VD, 90 microvolts, and then V out though 18.
Okay.
So
remember, when you go above, if you go above 75 or minus 75, it goes to saturation.
Okay.
So saturation is 15 maximum according to this one right here. You got saturation either negative 15 or positive 15.
Right.
Okay. It cannot go more than that. Yes, that's the cutoff for this this op amp.
Okay, and that would be true also for number 4.
Yeah, correct. Because you got negative.
That would be negative 15.
Yes.
Okay, so that was the issue.
Okay, you got it. Okay.
So we could never have a V out higher than the saturation.
Yeah, exactly. Depending on how the design is, they always tell you what is the maximum possible for the circuit. It's either positive 15 or negative. Some would be a little bit lower, but usually you look at your sheet and it tell you what's the maximum possible.
Okay, cool.
Okay, Nicholas.
Okay.
All right. Excellent.
I had one more question too from another assignment.
Yeah, sure. Go ahead.
Number 17, assignment 17.
Okay.
This is for like questions. Well, for a few of them, it talks about comparator circuits. And I went through all our handouts and the lab volts. I didn't see anywhere that directly stated anything or identified anything as a comparator circuit. I was just curious where that is in our, homework handouts. Yeah.
Yeah, I think Mr. Pham did mention. Mr. Pham did mention on that. Let me see. I forgot which one it was. It's been a while. It's op amp differential. I think either differential. I think it may be in differential amplifier circuit. Okay. Let me see. So you're doing comparator.
Yeah.
Let me see. I think. Yeah, it would say. I think he did. It's stated on the handout. Okay, so sort of something like this, comparing one to another. Yeah, it's similar to that. Let me see. Okay, so this one is not the one.
Yeah.
Okay, so yeah, it's I believe it's it's the one that's somewhere down in this area. I remember going through it. Okay.
Okay. Oh, differential
so-
amp.
Okay, yeah, I have to go
Oh,
look
geez.
through it one more time, just make sure to look through that. Okay, so you said about the comparator circuit. I can bring that up on next time
Okay.
we meet. Okay.
All right. All right. Thank
Alright.
you.
You're welcome. Thank you. Okay, anybody have any other question or? Okay, so pretty much I'm pretty much updated on everybody situation. So for Tech 1, this is what I have for pretty much everyone for as of right now. So right now we want to make sure that you so like I said, the first 10 was to be uploaded. So the next 10 should be up to around 15. So up to assignment 15 need to be uploaded to the website as for everyone. And so we should be by now, all the assignments should be up to number 15 should be uploaded to the website. Okay. And all these new couple of other new one that's coming up, those you can keep on working on it, and those gonna be due by the end of May. Okay, so we're starting the month of May, so so everybody should be starting assignment 16, 17, 18, 19, 20. Okay, so that's for Tech 1. For Tech 1. Okay, so this is what I have. So if you look at up to, so like Tim, you're doing pretty well. Oops, yeah. So you got everything. So up to 15, you're good. And Hernando, you already you at your pace. Nicholas, you're doing pretty well. And okay, so and we got Jose. You're doing pretty good. Look like number 14. Look like you may have 14 is missing. So
Yes, I'll upload it today. Thank you.
okay, thank you. Okay. All right, so Louis, you're doing pretty well. So just keep it up, okay? So yeah, everyone look like everyone. So most people. So we got 4 students that are able to get 4 or 5 students able to keep do the pace with the class, and a couple other students need to step up a little bit. Okay. All right, so that's for Tech 1, and for Tech 2, this is what I have currently for Tech 2 student. Okay. Jennifer, I was there compile errors on them, your DLab 7 and DLab 8, and so you can fix those and re-upload it to the website, and then I can be able to run the test on those. But as of right now, I can't run on it because it had compile errors. Okay, any question, anyone?
Yes, I've been trying to do number 14, but I can't get the numbers correct.
Okay, all right, Louis, let me see. Okay, assignment 14, let me go ahead and close this one. Okay, so assignment 14, assignment 14 would be this one here. Let me look at that just a bit. Okay. Let me minimize this out the way. Okay, so assignment 14 is deal with MSIM. Okay, M simulation. Okay. All right. This is what you have, right?
Yes.
Okay, so it's going to be just this one. We do the calc. Okay, so MSIM. Okay. So file open. Assignment 14. Okay, assignment 14. Okay, so something like that. Okay, let me increase that just a little bit, and we'll just shrink this one over. Okay, so we're gonna be looking at that. Okay, so we're gonna be so you want to do just turn on your generator. Okay, so turn on your generator, and so you want to do is, in this case it's going to be your VN for your generator is going to be 10 millivolt peak to 10 millivolt peak to peak. So you turn it on, and then it goes into frequency, and then you click on the amp to go to amplitude. Okay, in this case we need to get to 10 millivolt. Okay, so in this case, I cannot get down to a, it won't go, let me go down less than that. It looks like it's only stay 100. So what I do is just on my keyboard, okay, I just tap 0 and that would zero that out. Okay, so now I have to do is just look at this one. It's going to be moving my cursor to the right 2 spaces. Right here would be represent the 20 millivolts. So therefore I click on this one, this arrow to the right, 1, 2, and you come here and then you type in 2. I'll turn the roller here to 2. Now I just like to type in, I just type on my keyboard, okay, to press 2, and that's, they change it to 20 millivolt. Okay, is that your problem or setting that up or?
Yeah, that's also that, but I don't know which one to use to be able to go and get all the numbers and stuff like that.
And then you just have to do just follow what they need to look at calculation wise. So first thing they do VE. So turn on your oscilloscope. So this is your that there. Okay, so this is your oscilloscope. Now they want at VE. So this one they use DMM. So therefore this one with DMM. So turn on, and we need DC first. And so that DMM would be this one right here, the second one from the bottom. Okay, so we want to switch to DC and we want to measure VE. So VE, E would be down here. And the common or the low side would be need to connect it toward the closest to the ground. Okay, so and that's VE, and then you turn on your simulation to collect your data. Okay, so as you can see, negative 638.32 millivolt, and so we want to convert it to volt. So take this number divided by 1000. So mine came up a little bit lower earlier, so that's why it's a little bit. Okay, so that's 0.6. Oh, because I put in this one here, 20 millivolt. Should be 10. So that should be 10 here. Okay. All right, now we can look at. Okay, so it's, yeah, should be pretty close to that number. So that's what you do. You just do your connect, you just connect and measure and get your answer and then turn it off, disconnect, move into the next one, and so on and so on. Okay.
Got it. Yeah, I see what I was doing wrong.
Okay, and then you do. Okay, just read the instruction and say what it is, so what tools that you have to use to do your to get the answer. This one over here, they said to do the following calculation. Here you do the calculate, so it doesn't have to do any measuring. You just do your calculation with the formula. And here it said to use the oscilloscope. So here the oscilloscope. So therefore now I can close this one out and use the oscilloscope. So now I'm using oscilloscope. So they want to look at the VN. So VN is coming directly from the input. So we're going to connect it to channel 1. So somewhere in the input here, I want to look at my input. Okay, so right now it's like very, very small because this is set at 5 volt per division. This one had 10 millivolts. So therefore I need to decrease this one smaller. Okay, there it is. Now I can get start at 5. Look like it's pretty good. Okay, 2 looking even better. Okay, so somewhere there, stop, just do a single. And then you want to do, just go to your quick meter. And then you want to do is find out peak to peak. So click on peak to peak. And there it is. They give you 10 millivolt peak to peak. So you just put the answer there for VN. Next one, you move it to VC. The next one, you move it to V out. V out will be somewhere here. Okay.
Got it. Appreciate it. Thank you
You
very
can
much.
go
Sam.
from, you can go from there.
Yes, I can.
Okay, excellent. Okay. All right. Any other question? Any kind of concern with the homework? Okay, no question. Back to you, Mr. Pham. Thank you.
Thank you, Sam.
You're welcome.
Hello, everyone. Okay, first thing, you get any question to me?
How do I sign up for summer school? Luis.
What? Go ahead. Okay, so normally you see the quiz. Basically, you already done for electronic last or before last semester. You did a good job. So basically, we don't care on the quiz for each semester later on. The purpose is try to review to you. You can try to do without looking in any information, and you still get A. That means you're okay. That will helping you to get a job when you get an interview. Sometimes you get passed through one time, that's not enough. Like you study, reading one chapter one time, no way. You can have to read over. That maybe can help you to understand it. Okay, Sam did very good job. That will be helping you to review. Okay, we try to helping the student in order to be a technician, in order to get a much better job. We're not trying to fail anyone. Okay, if you want to learn, only thing is some can get our school sooner or later, depend on what you did in the program. And also when you get a job or get an interview, most companies will be asking in the program to see how the guy do it. That's what normally I have to do it. So how I couldn't remember most of the students in the program. So that's why I have to looking into the history to see what you did in order to return on the question to them. Okay. Finally, I want everyone working hard will get a better job and keep moving up. Someday you can get what you want. To me, I believe anyone can do it, then I can do it. Only thing I don't want to do it, okay? So let me share my iPad. Some in the program, I'm not going to that yet. The thing is that is not important. Will be get after we already done something you must know. Okay, even take one or take two the same thing. After we done, that's what I want you have to know. Then I can go back with something we left over. Okay? Just a minute, okay? Okay, sorry. Okay, last time we already talking about JFET DC bias. That's just telling you either bipolar transistor or JFET transistor, they need the DC power supply to make the transistor working. But the purpose using transistor is normally at the amplifier, either bipolar or JFET. Without DC power supply, the circuitry not working. And when we're talking about DC bias, then you have to memorize how many different ways we can bias the JFET. The first, they will be fixed bias. The second one, cell bias, and the next, power voltage divider bias. And the last one we don't care for now. So when you're looking into the JFET, then you need to recognize, is it a DC fixed bias or cell bias or voltage divider, and how to do at least minimum the calculation. For the cell bias and voltage divider bias, to solve the problem, they need the graphic for the train conductor. However, that's not they're using all the time. Normally, they given some different value, and you can solve without using the graphic. Okay, and today we start with the amplifier. The JFET are commonly used to amplify a small AC signal. One reason for using a JFET instead of the bipolar transistor is that very high input impedance Zin can be obtained. That's a difference. Okay. Sometimes they need to deal with the input impedance. If you remember in the past for the bipolar, you can get same thing, 3 different configuration: common admitter, common collector, common base. If you're looking in it back, you can see some circuitry on the bipolar, they get a high input impedance. Some they get a low input impedance, depend on the application. However, for the JFET, they will be telling you they get a very high input impedance. Okay, the reason they get a high input impedance, the thing is they don't want to loading down the signal coming. Okay. However, the big advantage, however, is that the voltage gain AV obtained with the JFET is much smaller than the bipolar. Okay. If you want to amplify, then you not using JFET. The thing is, they don't have a much voltage gate. And you have to using the bipolar. And the bipolar, you understand, you get a CE amplifier, CC, and CB. And the gain, you want more gain, you have to using the common admitter.
Is it possible to use a buffer for the low voltage to try and increase the voltage output?
Now, buffer is not try increase any voltage. Buffer come in. Whatever come in, they coming out.
So would there be a possibility for the circuit to have the voltage increased and still use the JFET for the high impedance?
Maybe you have to adding more state.
More JFET, more
Right.
speed, right?
Right,
So
more state.
what's the lowest or the smallest AC signal that you're aware of that the JFET can amplify?
Yeah, you can see in going down now. They're telling you normally what the voltage apply to the input of the amplifier, JFET amplifier.
So it can amplify lower than 1K then? Or 1 hertz? Can it amplify lower than 1
No,
hertz?
that's not talking about frequency. We're talking about the amplitude voltage.
Mainly voltage.
Yeah, frequency, that I believe no problem.
So it's not necessarily used for noise on the line amplification. Say if you have a very your signals from far away, like thousands and thousands of miles, and the signal is very low, and you want to try and amplify.
Yeah, they have to get some different circuitry, try to bring up the signal to the minimum so they can working with the other circuitry.
Right.
Okay,
Yeah.
that's a different. Okay, so you get a three, same thing like bipolar. In the JFET, you get common source CF, common drain CD, and common gate, same thing. Okay. Now, this will be applied for anyone want to learn detail in the AC analogy, either bipolar or JFET. First thing, set on the DC source to 0. That means you don't see any DC source in the AC module. They route it and replace them by short circuit equivalent. Second thing, replace all capacitor by a short circuit equivalent. So that's why when you're looking into the DC circuitry, you can see the capacitor C1, C2, or C3. Okay, but in the AC, you didn't see any more capacitor. They will be shorted, just like the wire. Number 3, remove all elements by short circuit equivalent. Okay, and introduced by step 1 and step 2. Redraw the network in a more convenient and a logical form. Okay, so that applies for either bipolar transistor or JFET transistor. Now, you can see this is the JFET P channel, N channel, P channel in a DC circuitry. However, for the AC module, you didn't see that anymore. They substitute by this one. That will be gate that will be the drain, and that will be the source. Okay, and between the drain and the source, you can get the current source. The value will be Gm times VGS. Okay, and then you can see this resistor here. That's what they call a internal output resistance of the JFET. That means this will be inside the JFET, and they will be very big. So that's why they not to deal with that small d. Okay, basically you can get only from the drain to the source a current source value will be Gm times VGS. Okay, let's see. FET input impedance. That means input impedance, that means you're looking into the input of the JFET. You can get a very big resistance. And they really want it to be infinity. Oh, FET output impedance, GL, okay, will be the right here, if without any connection, okay, where you can see gamma OS is component of an admittance equivalent circuit, normally at a rest of 10 to 50 microsiemens. That only telling you that's a very big resistance. Okay, JFET common source amplifier. The first one will be learning common source. Okay, when you're looking into the circuitry, we need to identify something. First thing, what the DC bias circuitry apply to this circuit. You understand, you get three different. Fixed bias, cell bias, voltage divider bias. So which one? Which one apply to common source amplifier now? What common? You have to tell me which DC bias.
Fixed bias,
What DC bias? Which one?
source.
No,
There's a fixed bias.
exactly. That's what. Answer my question. The thing is, before you want to do a amplifier, you have to get through the bias, DC. And again, you're looking into the circuitry. You must know, is it a fixed bias, cell bias, or voltage divider bias? That's a very basic thing you don't know, then they couldn't trust you, okay? If you learn electronics, you have to know, okay? So using DC bias for this circuitry will be a fixed bias. And I say can be cell bias or the voltage divider bias. That try to helping you to memorize, okay? Input signal apply to the gate right here, V in, apply to the gate. Output is taken from the drain. And also input, output will be our phase. Input positive, output negative. Input negative, output positive. Okay. So again, when you're looking into the amplified circuitry of the JFET, you have to recognize, is it a short bias, drain bias, or a short amplifier, sorry, or drain amplifier, or the gate amplifier. Okay. And next one will be C1 and C2. Normally, what is the name of the C1 or C2 in this circuitry? Telling me the name. C1 is what? Oh, let me know.
DC blocking,
DC blocking or AC coupling. Okay, that's the name. The purpose of the C1 is they only allow AC can go to the gate. Any DC from V input here cannot go to the gate. C2 the same thing. You understand the C2 will be DC block. The thing is at the drain in here, you will be get two different voltage. One voltage DC bias, and another voltage will be amplified of the input signal. So the output coming out, normally they can go to the speaker or the other device, but they don't want any DC. They want your voice only, AC only. So that's why we have to get the C2 to block any DC from the drain. Okay. And the other thing we need is the input output impedance. Input impedance, that means from the input here, you're looking into the amplifier. How much resistance you see, that will be input impedance. And from the output here, you look into the amplifier, see how much resistance you get, that will be output impedance. Yeah. That's a general picture. We're not talking about any calculation yet, but at least you have to memorize, okay, in order to be easy to get a technician job. So any question up to this point?
And also don't rely on the 50 ohm resistor in the generator, correct? Because that's technically not a DC blocking resistor.
No, nothing. You're talking about output generator,
Correct.
right?
Yeah.
Yeah, that's for generator. Normally they're using 50 ohm. But the circuitry, depending on the circuit. If you're looking into that one, can you tell me what the input resistance, which one of this common source amplifier? If you're looking on from the input into the amplifier, what you see? You will see that one. G in the DC bias. I already talking to you. Okay. Normally V voltage at the gate and the voltage at the VGG, they will be the same. Okay. If you look into the circuitry, this resistor will be very big. So that means no current can be flowing through RG. So the voltage between VGG and the V gate will be the same. If you don't want VRG here, you can short it here. Take it out, short it. They're still working on the DC offset.
Usually,
DC bias.
usually mega ohms that are real high, right?
Yeah, higher at least 1 mega. However, for the amplifier, if you don't have a this resistor here, when you convert it to the AC, this will be short to the ground. So the side wire going to the gate cannot go through the amplifier. Everything will be short to the ground. So that's why you must get this resistor, okay, to prevent the signal be shorted to the ground for the AC. Now, let's see what else. You see that? They draw a little more. This is the JFET internal. Okay, we don't care R small d anymore. You get only one current source going from drain to the source. And now you can see here, no more capacitor shorted, and no more DC shorted. Okay, see, battery VGG replaced by short. And capacitor C2 you didn't see anymore, just like the wire, they shorted. Okay, and also battery VDD also replaced by the short. However, from the drain, okay, you get the RD. So RD now will be shorted to ground. Okay, so if I'm looking into this circuitry, I can see what Y in input impedance equal, easy to recognize, they equal RG. And if you want to see the output impedance here, when you look into the amplifier, you can see they will be RD.
What does our
Yeah,
what does RG bias most, DC or AC voltage? Because it's technically trying to pull residual voltage to ground, correct? So it's
on
like
the power,
cleaning the line, right?
right? Just draw like the line. No more. You can see VGG, you don't see anymore. Just like the wire.
So the higher the resistor, the better. The measurement.
What do you mean measurement?
Well, if you can go higher than 1 meg, 2 meg, the higher the better, right?
That basically that depend on designer. Okay? When they designer, they decide. However, they must be high. And how high, that doesn't matter. If you are a designer, engineering design the circuitry. That's what you have to play with that.
That depends on what you want to try and amplify then,
Exactly.
right?
Normally that design will be more easy now. Okay, I can give you a simple thing. When they want to design the amplifier, they given you the input signal and voltage and the frequency, and then they asking for the output signal and the frequency. That's what they give it to you. Your job now will be try to design the amplifier to meet the requirement. Now more easy. Why? The thing is you can use in the simulation. Okay, you can get a basic circuitry for simulation for that amplifier. Then you can monitor between input and output you get. So in order to meet the requirement output, that's what you play with the input signal, you play with the RG, or you play with the RD to get the requirement.
So you can make a custom resistor. It could be like 1.34 or something like that. Very sensitive.
Yeah, anything
Right.
to get the requirement. However,
How excuse me, Mr. Fan.
yeah, go ahead.
How is the impedance being adjusted by the percentage of the resistor RG's tolerance? I mean, one going towards the JFET and back to the generator. Where's the most sensitive area of the signal?
No, depending on, what input impedance you want. Don't using the port. The thing is that normally they connect into the circuitry into the system. They don't want to tune in any resistor, that manual intervention. That's what they don't want it.
So it depends on your filter and what frequency you want.
Yeah, that depends on the requirement.
And you just want to clean the frequency up. No, I understand the what filter you want to use. It has a lot to
Yeah,
do.
that doesn't matter. But only thing is that's a very simple thing for any designer. They given you input and they want the output. You have to design the circuitry doing that, no matter which way or how.
Thank you.
Okay, now you can see common source amplifier. They want to calculate the voltage gain. Okay. And you can see if you want to calculate the VO right here, you get the current source here. Okay. And you get the impedance, output impedance. In this case, they say equal R big D. We're not talking about R small d. So you want to calculate the VO, you take the voltage times the current. However, you can see VO at here. That means the voltage measured from drain to the rail. Okay? Measure this way. Okay? And also, you can get the current. Okay? GM times VGS. Basically, they opposite to the VO. So that's why VO will be equal minus GM times VGS times RD. That's the voltage here. And the VGS, okay. And now you want to calculate the VAV, voltage gain. Voltage gain means the ratio between V out and V in. Okay, you take the V out, divide to the V in. So that's why you get a minus GM times RD. Now, when you calculate it for the DC bias, then the gain they will be negative. Okay. However, for the AC, you don't have a negative. The reason is the negative side just telling you input, output will be out of phase. That means input positive, output negative. Input negative, output positive. If the load included, then AV will be minus GM times RD parallel with RL. If the output here, you can get the load resistance. So you have to calculate the combination RD parallel with our load. So that will be, hopefully can make you clear to understand how to calculation minimum thing. That means calculate the V out for common source, okay? Calculate the gain voltage of the common source and the relation between the input and the output signal in phase or out of phase. Okay, any question up to this point? Okay, now I try to see. We can do this example. If you're looking into the circuitry, they will be common source amplifier. Okay, using the fixed bias. And they said the fixed bias configuration of had an operating point defined by VGSQ minus 2 volt and IDQ equal 5.625 milliamp. Okay. Now, why they have to go in given to you a IDQ or VGSQ? Okay. The reason is that for the DC bias. Okay. And that will telling you you don't have to do DC bias calculation. They already give it to you. Okay. So the first question is, they want to know what the GM equal. What the GM formula? You know, remember the formula for the GM. What GM equal? Okay, who tell me?
GMO times 1 minus VGS over VGS off.
Okay, that means you say ID at that, right?
GM equals,
Oh, GM equals GM0, right?
correct. Divided by 1 minus VGS over VGS off.
Okay. GM0 times 1
Minus
minus,
VGS over VGS off.
okay. Not square.
No. At
Now,
least by the formula.
yeah, the thing is, you have to remember the basic formula that they don't have a many. Okay, they get the ID, VGS, okay, GM0. What GM0? GM0 equal what? You get 2 times IDSS.
I'm working on it.
Man,
Divided by the absolute value of VGS off.
that's a minimum formula. Try to memorize it, okay? They will be asking you. Even they don't want you to do calculation. Normally, next question is, what is the GM0? What I said, you want to be a technician, you have to reading the handout over. If I asking your guy a question, you not answer it, I not want to go anymore. You have to be cooperate with me. Telling me the one I'm doing is good for the student. Okay, tell me what the GM0. What is GM0?
It's the value of GM when BGS is equals to 0.
Exactly. GM0, that means the value of the train conductor with the VGS equal 0. And normally they be given, okay, in the manufacturer. Okay, on that one, I don't want you to calculate the number B, RD. R small d, just internal resistance of the output of the JFET. If you're going back, you can see the formula, but it's not basically will be using anymore. Anyway, so we don't need to calculate the number B. Okay. Number A, you have to do calculation. So the first thing you need the GM0. and substitute into the formula calculator GM, you can get it. I just want the answer for number A. So for some students, they couldn't get it. That will be help them to redo calculation. What GM equal?
So your GM should be come to 1.875.
Okay. You get a 1.875. Milli, right?
Yeah, millisiemen. Simon.
Anyone else get the same answer?
JFET.
Okay. You understand? Sam been working for me for a couple of years. After he complete this program, and we offered to him to working with us. And now he did a very, very good. The job in the program. The reason they have to go over and over. So that's why on the review for the quiz have a lot. Okay. So if nobody can get the answer, he given the answer. If anyone get the same, let me know. Otherwise, we're supposed to be that a good one. Okay, input impedance, C. What equal?
1 meg. 1 mega ohm.
Exactly. That means you're looking here, you can see input impedance here, you get a resistance here. What output impedance?
2K ohms.
2K ohm. Perfect.
Excellent.
What the voltage gain? So basically, we don't want to calculate E. That means they want including in internal resistance of the JFET, and we don't want to do it. I want number F.
3.75.
Okay,
You got it, Michael.
3.75. Perfect. Okay, so for common source amplifier, when you're looking into the circuitry, you know this is common source. Where they apply input to what are the output supposed to be, from where, drain or gate or the source. And also what the type of the DC bias will be using. Okay. And also when we deal with the amplifier, we deal with the GM and GM0. That's the formula you need to know. So up to this point, any question? If you are able to understand what we try to happen you here, when you go to university, you don't have a much problem. This is a very, very basic thing. Okay, engineer have to get through it.
I got a question.
Go ahead.
And what do we see all this in?
What do we see? What?
Like the components on like the whole entire structure that you have here. And like what devices can we see that in?
What devices?
I would say like a computer, a tablet, or a phone.
Radio.
No. You're talking about the application. You see what I'm saying? That means you want to know they will be using in the phone or in the computer or in anywhere. But that is very general in detail. Okay, the course will be teaching you. Only thing is, if you deal with the JFET minimum thing, you have to know. And the application, if you see on the cell phone or in the some radio in the anywhere electronic circuitry, you're able to recognize. That is the circuitry will be using JFET or using bipolar or using anything else. We cannot tell you.
Okay. Yeah, because I'm like a little lost and I'm trying to like find out how can I use it or where can I use it at?
No. Do not supposed to be say how come you use. Okay. Only thing is when you're looking into the circuitry, you have to know what we already talked to you. What different circuitry, what the name of the circuitry, what the circuitry try to do. Okay. Like you want to amplify the signal. You can using bipolar or JFET amplifier. If you want the input output to be opposite for the JFET, then you have to using common source. Don't think too far away from that. That's the minimum thing you need to know. Sometimes I understand you want to know that in what the application they're using where. And they can using anywhere if the requirement needed. Like they want high input impedance, okay? And they don't want much gain, then they can using the JFET amplifier. And the JFET amplifier will be depending on their circuit. in the program. That's what I only want. You looking into the circuitry, you have to tell me. Okay.
Okay.
Yeah, I see some student on the chat telling what the application. Okay, I have no idea. Will be JFET, will be using, okay, anywhere. They can be using anywhere when they need or when they want to meet the requirement for designer. If you go university, they will be get a course for designer of the bipolar transistor, JFET transistor, okay? Then they will be teach you how to do it, okay? The thing is, one my student, two students in a graduate on 2019, and he at the San Diego University now, and he graduated on the end of this year. Okay. The thing is, when he went into the University of San Diego, I contact with him all the time to see what they teaching, what the course they offer. Okay. The thing is, I graduated 1980. That's too far away from now. Everything up to date, basically the same, but not different. So that's why I want to know. And I recommend to him which one better take, okay? And also, I try to get on document they teaching up there. If you want to learn in that course how to design bipolar transistor, JFET transistor, then they will be telling you. Okay, anyway, it's time I stop my and Sam try to run the quiz, okay? I stop it now.
Okay, sounds good. Okay, let me go ahead and set it up. So make sure you download the quiz number 6. We're going to be going through quiz 6 today. Let me see quiz number 6. I got open. Okay, so quiz 6. Quiz 6, tech 1, quiz, no, it's quiz number 6. Number 6. Okay, so let me go to share screen. Share screen. Okay, so all right. Here we go. Slideshow. Start from beginning. Okay, can everyone see my the PowerPoint presentation?
Yeah.
Okay. Okay, so that's pretty much it. And so make sure you upload it before 12 noon tomorrow. Okay,
Thank you. Have a good evening.
you're welcome. Have a good evening. All right, let me
Okay,
see.
you Sam.
Yeah, you're welcome. Okay.
Okay, any more question before good night? Okay, so no more question. Good night, everyone.
Good night, Mr. Pham.
Thank you, sir.
Good night.
Good night.